Okay, so we're going to talk about something called heating curves. So we are going to be calculating the amount of heat energy that it takes to change the temperature and the phase of a substance and take it from one temperature to another temperature. So like we mentioned in another video, you cannot calculate the amount of energy it takes to change the phase and the temperature at the same time. So those are separate steps, and we're going to see how we can calculate the total energy of the whole process by adding those individual steps together. Before we do that, let's just take a quick second and talk about the three phases of matter that we're talking about in this class. So we're talking about solids, liquids, and gases. So we can go from a solid to a liquid or a liquid to a gas. And this process is called the heat of fusion. So I'm going to say delta H FUS. So that's the enthalpy of fusion. That's how much heat it takes to go between these two processes. And going from a solid to a liquid, you have to put heat in. So this would be endothermic. And going from a liquid to a solid, this is removing heat. This would be exothermic. So, and then from a liquid to a gas, or a gas to a liquid, this is called the heat of vaporization. And again, going from a liquid to a gas, you have to put energy in. So it would be endothermic. That you're removing would be exothermic. This is why sweating cools your body down, because as you go from a liquid to a gas, you're removing heat and that cools your skin down. So this is what is happening here in our phase diagram. And we are going to be talking about changing these phases. And I didn't want to just skip over this, but this is something that's in your textbook, and heat of fusion and heat of vaporization are what we'll talk about. There is actually a process of going straight from a solid to a gas. That is called sublimation. There is a heat of sublimation that we won't talk about. It's actually the heat of fusion plus the heat of vaporization. And then there's also a process of going straight from a gas to a solid, and that's called deposition. And that's just the same thing, heat of vaporization plus the heat of fusion. So this is what we're talking about. I'm going to write out what the problem would look like, and then we'll go through this thing called a heating curve. You also could have what's called a cooling curve if you were going the other direction, but in this case the temperature is increasing, so we're calling it a heating curve. Okay, so I'm going to say how much energy is required to change 100.0 grams of ethanol. Ethanol is C2H5OH from negative 150.0 degrees Celsius to positive 150.0 degrees Celsius. So how much energy does it take to take 100 grams of ethanol from negative 150 degrees to positive 150 degrees? So that's the question. So before we can do anything, there is a lot of information that we need, and it all is going to be specific to ethanol. So I'm just going to write that down for you, and then you would be able to look this up if this was a SmartWorks problem and they were asking you about some other specific substance. You would use these points specific to whatever substance you're using. So for methanol, the melting point, which I'm just going to abbreviate MP, the melting point, so that would be the point between solids and liquids, is negative 114.0 degrees Celsius. The boiling point, where we go between a liquid and a gas, is 78.0 degrees Celsius. the heat of fusion for ethanol is 4.60 kilojoules per mole. The heat of vaporization is 43.5 kilojoules per mole. And now we're going to get all the specific heats. And there's a specific heat for ethanol for all three phases of matter. So the specific heat for solid ethanol is different than the specific heat for liquid ethanol or for gaseous ethanol. And you would be able to just look all of these up. So for solid ethanol, it's 2.419 joules per gram degree Celsius. For liquid ethanol, it's 2.46 joules per gram degree Celsius. And for gaseous ethanol, it's 1.70 joules per gram degree Celsius. Okay. So this is all important information that you need to be able to draw your heating curve. So the first thing we're going to do is we're going to draw the heating curve to see what it looks like. So the shape of this heating curve is going to be generally similar for all substances, but these melting points and boiling points, we call these critical temperatures. These are where the phase changes happen. So if you were drawing the heating curve for water, the melting point of water is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. The overall shape of the heating curve between ethanol and water would be similar, but they would just be on a different scale, just on different places on the graph. So I'm going to go ahead and draw this. This is not to scale. There are actual examples of these in the textbook, so don't get too fussy with it. So I'm just going to say this is negative 150 degrees Celsius, and this is positive 150 degrees Celsius. So this is going to be a scale of temperature in degrees Celsius, and this axis is going to be the progress of the reaction. Okay, so we are starting at negative 150 degrees Celsius. It doesn't melt until negative 114 degrees Celsius. So I'm going to say this right here is a negative 114 degrees Celsius. This is the melting point. So from here to here, we're going to say, this is, I'm going to call this step 1. So this is where we have, what's happening at step 1, I'm going to write it over here, is we have solid ethanol. I'm going to abbreviate ethanol. Well, I'll just write it out. Solid ethanol, C2H5OH. And we are changing the temperature from negative 150 to negative 114 degrees Celsius, degrees Celsius. So that's what's happening in step 1. Now that we're at 114, we're not changing the temperature. What happens at 114 degrees Celsius, I'm going to call this step 2. This is the melting point. So this is the point where we are changing phase. We are changing from solid to liquid. So remember we said you cannot change phase and change temperature at the same time. So in this first step, we're going to calculate, we'll do calculations for each of these steps as we go. In this first step, we're only calculating the amount of energy it takes to change the temperature. At the second step, we're only calculating the amount of energy it takes to change the phase. We're not changing the temperature while we're changing the phase. So now we're at 114 degrees Celsius. The next thing that's going to happen is we're going to increase the temperature of this ethanol until we reach the boiling point. So we're going to go all the way up to 78 degrees Celsius. We'll say this is 78. So we're going to call this step 3. So what we're doing in step 3 is we have, and put parentheses around that, we have liquid. From here to here it's a liquid because we just melted it here at the melting point. We have liquid ethanol, C2H5OH, and we are changing the temperature from negative 114 degrees Celsius to the boiling point, positive 78.0 degrees Celsius. So that's step 3. Step 4, now that we are at the boiling point, now we are going to change the phase again. We're now changing the phase in step 4. This is the boiling point. We are going to change the phase, changing the phase from liquid to gas. So now at the end of this phase change, we have gas at 78 degrees Celsius. We're going to 150 degrees Celsius, so that's going to be my last, step 5. We'll say that's 150. So here's step 5, and what's happening at step 5 is we have gas, gaseous ethanol, C2H5OH, and we are changing the temperature from positive 78.0 degrees Celsius to positive 150 degrees Celsius. Each of these 5 steps is a calculation using either the specific heat or the heat of fusion or heat of vaporization. So another thing to pay attention to is that the units are different. The heat of fusion is in kilojoules per mole. The heat of vaporization is in kilojoules per mole. The specific heats are in joules per gram degrees Celsius. So we're going to be using different values for quantity and for energy. So I'm going to need to convert 100 grams of ethanol to moles of ethanol to use for these steps. I'll use the 100 grams of ethanol for these specific heat steps. I also am going to convert these specific heat steps also to kilojoules because in the end we're going to add steps 1 through 5 together, and that will give us the total energy required to change 100.0 grams of ethanol from negative 150 degrees to positive 150 degrees. Okay, so I'm just going to start from step 1 and work our way through. So again, step 1, 3, and 5, we are changing the temperature, not the state. For these equations, we are going to use the formula Q equals mass times the specific heat, remember the specific heat of that phase, times the change in temperature. So that's what I'm going to do right here. And it's going to give me an answer in joules. I'm going to convert it to kilojoules so I can add it all together at the end. Okay, so here is step 1. Q equals mass times specific heat times the change in temperature. Okay, Q equals mass, 100.0 grams, times the specific heat. I'll go ahead and put the S here because we're solid, it's frozen. So right here, 2.419 joules per gram degrees Celsius times the change in temperature. So how much does the temperature change? It's going from negative 150 to negative 114. So that's 36 degrees Celsius. So 100 times 2.419 times 36 is going to give you 8,708.4 joules because grams will cancel and degrees Celsius will cancel. But I know I'm going to need to add all of these up later, so I'm also going to just go ahead and convert this right now to kilojoules. 8.7084 kilojoules. So this is step 1. So that's how much energy it takes to just do step 1. To warm up ice ethanol solid from negative 150 to negative 114. It's still a solid. So now here at step 2, we are changing the phase, not changing the temperature. So for here at the melting point, I'm going to use the heat of fusion. I'm going to use the heat of fusion times the number of moles, because the heat of fusion is kilojoules per mole. If I multiply by the number of moles, then I will get the heat. So heat of fusion here, actually the formula that's in your book is going to say Q equals N times the heat of fusion, delta H FUS. So that's how I'll write it here. Q equals N. So I converted 100.0 grams to moles. The molar mass, I used the molar mass of ethanol, which is 46.07 grams. You can calculate the molar mass of ethanol from the formula of ethanol. And then I used it to convert grams of ethanol to moles of ethanol. And I calculated that there are 2.17 moles of ethanol in 100 grams of ethanol. So this is an important step. So don't forget to change this, convert to moles for steps 2 and 4. So it's 2.171 moles of ethanol. Okay, so 2.171 moles of ethanol times the heat of fusion, which is 4.60 kilojoules per mole. And for that, you should get an answer of about 9.982 kilojoules. So this is why I converted this one to kilojoules, because these ones are going to be in kilojoules. And most of the time, enthalpy or energy is in kilojoules, not joules. Doesn't really matter, but that's just the way you're mostly going to see it. Okay, step 3. So in step 3, what I'm doing is I'm converting liquid ethanol from negative 114 to positive 78. So I'm going to use this formula. Q equals mass times the specific heat of liquid ethanol, because that's what I have here is liquid ethanol, times change in temperature. So mass, 100 grams, don't forget you're using grams here and moles here, times the specific heat of the liquid, 2.46 joules per gram degree Celsius, times the change in temperature. So this is negative 114 to positive 78. So that's 192 degrees. From negative 114 to positive 78 is positive 192 degrees Celsius. So when you put this in your calculator, you should get something like 47,232 joules, but I'm going to add these together in kilojoules. So this is the same as 47.232 kilojoules. So that's how much energy that step takes. Okay, now let's go to step 4. So what's happening at step 4 is I'm just changing the state. I'm changing the state from liquid ethanol to gaseous ethanol. So I'm going to put it down here just so I have space. Q equals the number of moles times the heat of vaporization, because we're going from a liquid to a gas, so we use the heat of vaporization here. Here we're going from a solid to a liquid, so we use the heat of fusion here. So just pay attention to what's happening. Q equals N, 2.171 moles, times the heat of vaporization, 43.5 kilojoules per mole. And this should give you something like 94.44 kilojoules. Okay, so that's step 4. Now we have one step left. The last step is now we have gaseous ethanol, and we are increasing the temperature from 78 degrees Celsius to 150 degrees Celsius. So here we're changing the temperature of gaseous ethanol. So I'm going to say Q equals mass times specific heat of the gas times the change in temperature. So Q equals 100.0 grams times the specific heat of a gas, 1.70 joules per gram degree Celsius, times the change in temperature, which is 78 degrees to 150 degrees. So that is 72 degrees Celsius. So when you multiply this together, you should get 12,240 joules, or 12.240 kilojoules. Okay, so to calculate the amount of energy that it takes to go from negative 150 to positive 150, you have to individually calculate what's happening at each one of these steps and add them all together. So when I add step 1 through 5 together, and remember your number of significant figures is going to come from your question. So all of these numbers have 4 significant figures. Sorry, this 0 after the decimal place is definitely significant. 4 significant figures. So with 4 significant figures, the total should be 172.6 kilojoules. That's how much energy it takes for this whole process. And depending on how you may have rounded through here, your number might be a little bit different. That would be totally fine. So there's a lot going on here. I would definitely recommend that you come back to this in a day or so and try to do it on your own without all of my work filled in, and see what you can do. Also remember that not all of these heating curves are going to have 5 steps, because for example, if I said how much energy does it take to go from 100 degrees to 150, you would already be starting here as a liquid. So you wouldn't need to change the temperature of a solid or to change the phase from solid to liquid, because you would already be starting at a liquid. So the most important thing to do when you're starting these heating curve problems is to draw the curve first, and then see how many steps your problem is going to have. This is the most steps a heating curve problem can have, is 5, but it could have less depending on the range of the temperatures and what your critical temperatures are for your substance, your melting point and your boiling point.